The next talk is by Yexiang Xue from Cornell, and it's about Avicaching, a two-stage game for bias reduction in citizen science.
Okay, thanks. So I'm Yexiang, coming from Cornell, and today I'm going to talk about Avicaching, a two-stage game for bias reduction in citizen science, and this is joint work with people in Cornell Lab of Ornithology. So as you all know, eBird is a very successful citizen science project for collecting, bird observational data from a lot of bird enthusiasts. And we use this data coupled with remote sensing data and so on, and we are able to build today the most comprehensive and detailed species distribution models for hundreds of species across the Northern American continent and all over the world. eBird has been enormously successful. We have hundreds of thousands of participants, volunteered over hundreds of millions of observations into this data set. Despite its great success, eBird suffers from a data bias problem. So here on the left, I'm showing you a heat map of where the observations are for eBird in United States. As you can see here, almost every whale lights up in this map. But if you zoom into one region, you still find that most of the observations are centered around certain areas. In this case, they are in urban areas. And just to reassure you that this is not a single problem that eBird has, here at on the right side, I'm showing you for another citizen science project that we just launched in Eastern Africa in 2015. And Nathan Jensen is going to talk about this citizen science project in the following talk. And as you can see there, the purpose of that citizen science project is entirely different from that of eBird, but as you can see there, still the observations are centered around certain areas. It is not too hard to understand why there is a data bias problem in this case. To engage participation, citizen science projects often impose little or none restrictions about where and when the observations are collected. As a result, most of the observations are collected in those locations that are either interesting to people, such as national parks, state parks, and so on, or in those locations that are most convenient, such as in urban areas and so on. This poses a fundamental challenge for addressing the scientific goal of citizen science projects. Take eBird for an example. On a lot of these places where you have gaps in which you have no data at all, the scientific goal for eBird is to fit a species distribution model for using eBird data. For all those locations where you have gaps, you can't even validate your model. So this is going to be a problem. We introduced Avicaching. It is a very interesting game to basically use external rewards. In this case, they are Avicaching points to try to push people into those undersampled areas. So the game goes like this. Suppose there are no rewards, then the bird enthusiastic, they come and they would choose to go to their favorite places. And then we as an organizer, we offer some external incentives at those undersampled locations. And then the bird watcher comes again. He would, look at these external incentives, and he would potentially, shift some of his efforts into these undersampled areas. This becomes a game between an organizer and a series of agents. So we, as an organizer, we try to find a set of rewards that is going to minimize the spatial bias. And then the bird watchers are agents, and they see a set of locations. And each of these locations is associated with some intrinsic utilities for the bird watcher to go to this location. And then we, as an organizer, we offer some external incentives to some of the locations. And then the bird watcher will choose a subset of locations that jointly maximize their utility function after taking into account both intrinsic utilities and external rewards. On a high level, this is a bi-level optimization problem in which we have the organizer and agents. They both have their utility functions, and they are subject to their own budget constraints. And then the problem then becomes how are we going to solve this bi-level optimization? The challenge comes in the fact that we have a small optimization, the agent optimization problem, embedded in the global optimization. So a naive approach would enumerate all possible reward treatment, which there are exponential many of them. And then for each reward treatment, you would basically solve the agent optimization problem and then determine what is the benefit of taking that particular reward treatment. And then it goes through all the reward treatment and find the best one. And that method, of course, doesn't scale. So we need fundamental new approach. In our case, we actually develop a new approach, and the approach is by a change of knowledge representation. We actually rewrite the agent decision process from a procedure encoding into a declarative encoding. And in our specific example, in the agent model we consider, we're able to represent the agent decision process using a set of linear constraints. And then, before we have a bi-level optimization problem. Now what we can do is to fold in this linear constraint into the bi-level optimization problem, and then the whole problem becomes a single optimization, and so it can be solved by a off-the-shelf optimization package. We deploy our method as a game called Avicaching in Tompkins and Cortland County in New York State. Tompkins has a high participation rate for eBird, but Cortland doesn't. We identify a set of Avicaching locations, emphasize important landscapes, and all these locations are unsampled locations. They receive 0 visits before our game. We give people Avicaching points for their observations made in Avicaching locations. These points represent their contribution to science. We maintain a leaderboard, and birders have opportunities to win birding gales based on a lottery, based on how many Avicaching points they earn. Now the response are phenomenon. From April to October in 2015, we are able to shift over 19% of effort in these 2 counties from traditional hotspots to Avicaching locations. Here on the left, I'm showing you 2 graphs, and on the top of that is, where people submit their checklists in 2014 before the Avicaching game. And I'm contrasting that with a graph in the bottom, which shows the, where people submitting their checklists in 2015 when Avicaching is in the field. The shaded area are our study area, and the size of the circle represents how many visits are there into each of these locations. As you can see, most of the efforts are in Tompkins County in 2014, and in 2015, with the help of Avicaching Game, we are able to shift the effort to almost everywhere in these 2 counties. So to remind you that the core idea of solving the bi-level optimization problem is by a change of knowledge representation from procedure encoding to declarative encoding. And since then, I have been so fascinated by this idea. So in my most recent effort, I'm trying to apply similar ideas into solving the following problem that finds the optimal policy intervention to maximize an expectation of a probabilistic model. So this is a fundamental hard problem. To compute the expectation of a probabilistic model is often believed to be sharply complete. And we are going to do an optimization on top of that, which is another NP-complete problem. So this problem actually combines both the 2 hard problems, and is believed to be even harder than both Sharpie and NP hard problems. It has a lot of applications. So for example, corridor design to maximize the spread of cascade is a very nice example of this type of problem. Here the sum operator represents the expected spread of the cascade, and the maximization operator represents the optimal corridor design. And it also could have a lot of other applications in machine learning and so on. So the way we solve this problem is by rewriting this intractable Sharpie sum with a series of NP oracles subject to additional parity constraints. And noticing that NP queries can be written as optimization problems, So then we can do the similar folding trick to fold in this optimization problem into the global problem. And we are able to develop a constant approximation algorithm to solve these type of problems using this idea. So to recap, I introduced you Avicaching, a two-stage game at the intersection of probabilistic reasoning, machine learning, behavioral economics, game theory, and so on. We achieved a great field response. And the core idea to solve the bi-level optimization problem is by a change of knowledge representation to fold the agent optimization problem as linear constraints into the global problem. And this idea opened doors to a lot of novel algorithms and applications and so on. With that, I would like to thank you and take questions.
Thank you very much. We have time for one quick question.
So which fraction of these top birders work for the Lab of O?
Well, that is a great question. That is a great question. So for Avicaching, so what we discovered was 80% of the data are submitted by 20% of people, and so this is actually a phenomenon, quite prevalent phenomenon. And indeed, there are some of them who is the top 20 birders in these two counties work for Lab of Ornithology. But we do have like 5 of them. So out of the top 20 birders that participate in our game, we do have about 5 to 10 of them that are not working for Lab of Ornithology.
Let's thank our speaker one more time.